would like to thank the RIO committee and my dear friend Dr. Tarek for his kind invitation, and I would like to welcome my dear friends Cynthia Roberts and mentors in Egypt and on the podium. I will be as short as possible to present a new concept in, can I have my screen? A new concept in the refractive surgery, a paradigm shift that is going to change our practice a little bit. Let me start with our legacy in refractive surgery. All the maps that we have to design for refractive surgery is a kind of a printed lens, and the idea of the printed lens on the cornea, any refractive surgery, corneal reshaping or remodeling, comes from what is a tomographer or an aberrometer. Of course you know this, and of course I have hundreds of cases, maybe thousands of cases treated with a complex cornea by data, like waveform data acquisition from any aberrometer. I use the eye design one, but anyone can do the same to form this kind of irregular shapes on the cornea and to carve them. It's a lens printed, and of course to bring a very good results, as you see here. In such very complex cases, you can approach even the hemiptropia and provide your patient with a very good vision. Yet, we have some little problems with the aberrometers and the topographers that we have in hand in general. Like, for example, the crossovers who work with an aberrometer knows very well that the condensing of the aberrations can make one lens take the information of another lens, and this is called the crossovers. Also, the limitation of the pupil. When you have unlimited pupil size, there is an extrapolation of data outside or beyond this pupil that limits the results of the aberrometric guided ablation. And of course, the interdependence of the polynomial shapes. Polynomial Zebedee polynomials are shapes to describe the aberrations. All these are pitfalls. Everyone who works with aberrometers or tomography guided ablations know very well these facts. Let us come again to the complex cornea. The complex cornea, as a refractive surgeon, we think that it is rare. No, by statistics, complex cornea is not only, for example, ectasia and so on. It could be any mixed astigmatism, any hyperopia because of the issue of the angle kappa. Any even regular astigmatism by high one, it brings a kind of irregularities on the cornea. And of course, opacity, strigium, so on. So if you have an excellent refractive surgery center, you would have like 2/3 of your cases a complex cornea. Or in the population, in general population, it mounts up to 15 to 25% of the population. So it's a very big issue to have or to design a complex cornea. The genius of Michelangelo, and every one of us knows who's Michelangelo, the genius of the Renaissance of the art, he was able to imagine the ideal shape out of a block of marble and to bring such a beauty of David, which is the masterpiece of his sculpture, just by taking the excess out of the cornea. And this is what is the shape, the ideal shape that we're looking for. By taking or by getting a kind of high precision tomographer that will analyze the component of the most important refractive surface, which is the cornea, into 3 components, which is the epithelium, the anterior surface and the posterior surface, and the summation of those is what we see in action. And to do by the ray tracing principle, and to do the ideal shape, to not to carve on the cornea, but to take the excess from around it and to reshape the cornea once again. Let me show you an idea how the epithelium plays a role when you have an irregular cornea. It plays a very big lens to mitigate the irregularities in the anterior and posterior surface. And in the same way, also the posterior surface of the cornea, as you see, it is highly irregular when you have like an ectatic cornea or an area or a complex cornea. If you do these together, and this is taken by a high precision tomographer, as I said, and with a design of ray tracing to trace the light if it passes through these 3 layers of the cornea, and to reshape the cornea again to make them fall on the same side. Not only this, but by this that just shown now, an ideal pupillometer, which depends on an artificial intelligence system to make the ideal pupil for each patient, depending on measuring the idea of the pupil at different lighting conditions, and also to relate it to the profession of the patient. I mean, if the patient is a doctor, he will be totally different than a night driver and so on. And to have all these in the cloud, Why in the clouds? Because you can play with this planning at your office, and not only this will be the future of our practice maybe in the next decade, to do a remote surgery on your patient in another country. Last week, I operated on a patient in Italy from India. I mean, it could be like a science fiction, but it works. Because you just need to execute the plan from outside. So you can make, I mean, it's a kind of economic thing to buy just one machine in one center and to operate from other countries or other towns even. So the complex cornea simply will be broken down into its components of the epithelium, anterior surface and posterior surface, and to creating an ideal shape. Ideal shape is not only the way that you curve the cornea or taking the access to bring the light to the fovea, but also the connecting zone or the transition zone. It will not be one size fits all, because it's not logical to have the same transition zone above and down. You need to retilt the irregular cornea once again by reshaping the cornea and leaving on the anterior surface such an irregular cornea to mitigate the posterior one. So the idea of the ideal shape will be totally different, and will be also dependent on the pupil size. This is the reversing back of the what is called the ray tracing, and to relate it the ideal pupil size, which we define as the pupil that suits every patient, not one size fits all. And of course, we've learned from the Stills-Crawford effect that the most important part of our vision comes from the central 2 millimeters. So why not to make a refractive zone of 2 millimeters? But the idea is to carve the connecting zone in a way to take the cornea in a very regular shape from the center to the periphery. And this is what the new system is playing with. So this is the ideal shape. And if you look at this for an irregular cornea, you will see that the irregularity of even the connecting zone, just as you say here in the film, to retilt the cornea back. If you curve an irregular cornea on the anterior surface to guarantee that the light will come to the fovea and to recenter the cornea once again, it will be the same. I'll just a few seconds to finish. Our dear colleague Cosimo Mazzotta just published almost 1 year ago, his first work on retilting the cornea of the keratoconus by transepithelium ray tracing guided ablation, and followed immediately by cross-linking, which is again a feature in the machine to do an online cross-linking immediately, customized on the thinning zone. And we've seen the nice and beautiful lecture of Cynthia Roberts, how the zone is different in the keratoconus. We are targeting the zones of stress and the thinnest location, so you don't have to make a full corneal cross-linking. And he demonstrated clearly, maybe tomorrow I will demonstrate more cases, but he demonstrated clearly how you can do, like here, a 3 millimeter optical zone 3.2, and to curve the cornea in a very good way to bring such beautiful results. He demonstrated 4 lines of improvement in the uncorrected visual acuity, and in the, thank you for giving me some more time, and best corrected visual acuity of 4 lines. Can I have the last slide just to announce for our WPC? The last slide, and I can't, yes. So, I'm here to announce the WPC, the World Keratoconus Congress in June. We have the president here, Dr. Miltos Palides. We'll be happy to see you all. And again, next month in February, in 3 weeks from now, the Dry Eye and Ocular Surface Society in Brussels. Thank you very much.